Let's now use the course grade example to illustrate the effect of declaration and execution of a program. As discussed, the declaration of an identifier, in addition to defining its data type, it also allows the computer to do memory allocation when the program is executed. In this program, 7 identifiers, namely exam weight, lab weight, homework weight, exam score, lab score, homework score, and final grades are declared. I'll use this diagram, which shows a set of storage bins, to illustrate the allocation of memory when a variable is declared. This is for illustration only. A memory space is of course different from a storage bin. When a declaration of int exam weight is made, memory space is allocated according to the size of the data type, in this case int. The assignment of the value 70 to exam weight will initialize the value stored in the memory to 70. In a computer, the value 70 would actually be represented as a bit string of zeros and ones. The declaration and initialization for lab weight and homework weight would go through a similar process. The declaration for exam score would allocate enough memory space for storing a floating point number of type double. Most implementation for double would require 8 bytes, so the size would be different from those for int, which is 4 bytes. Similarly, memory allocation would be made for lab score, homework score, and final grade. I'll use different color here to illustrate that int and double have different memory requirements. Since no value has been assigned to these variables, their values are not known. In fact, they must first be given a value before reference can be made to them. After declarations are made, the program would ask the user to input values for exam score, lab score, and homework score. Assuming that the user entered 90.0 for exam score, notice that even if the user just entered 90 without a decimal point, the value would be converted to a floating point number. Again, I'm using a different color here to distinguish double type from int type, which is in blue. Similarly, a value of 85.0 is entered for lab score, and a value of 80.5 is entered for homework score. To continue the execution, another assignment statement which changes the value of exam score would be executed. The evaluation of the expression to the right of the assignment statement will first compute the expression inside the parentheses. It would retrieve the value of exam weight from the memory and then divide it by 100.0. Note that exam weight is an integer. If it is divided by another integer, 100, the result would have been 0. But since we are using 100.0, which is a floating point number, the result of the division would be a floating point number 0.7. The value of exam score would then be retrieved from the memory storage for exam score and multiplied with 0.7. The resulting value of 63.0 would then be assigned to the variable on the left-hand side of the assignment statement. The result of the assignment would replace the original value of the memory for exam score by the new value, which is 63.0. Similarly, the value for lab score and homework score would be updated, and finally, final grade would be computed by adding the updated value for exam score, lab score, and homework score. The resulting value of 88.05 would then be assigned to the memory space for final grade. During the program analysis step when designing the original problem, it was recognized that the weights for the exam, lab, and homework should be predetermined, and their values should be the same for all students in the same course. If we want to prevent the weights to be changed by accident, we may want to declare those identifiers as constants by putting the keyword final in front of the declaration. In a way, we can think of these as locking up the memory cell and disallow any attempt to change their values in other part of the program. Let's say if a student has done poorly in the exam but done well in the lab. The attempt to decrease the weight for exam and increase the weight for lab will be disallowed.